Hello, welcome to the CCNA study guide brought to you by Eduonix. This is chapter 1, video 5, which we're going to be predicting the data flow between hosts across a particular network. So here we have some routing protocols here, which are very, very common, especially used with Cisco devices. So OSPF, you may have heard of these already outside of this, but OSPF stands for Open Shortest Path First. It's a routing protocol for the Internet Protocol. So it's a routing protocol for IP networks, basically. It uses link state routing algorithm and falls into the group of interior routing protocols, which operate within a single autonomous system, which means that it uses hops to look for the best route to something. RIP routing, or the Routing Information Protocol, is one of the oldest distance vector routing protocols, which employ a hop count as a routing metric. RIP prevents routing loops by implementing a limit on the number of hops allowed in the path from source to destination. RIP v2 is actually an enhancement on RIP v1's features and extensions rather than an entirely new protocol. Some of the enhanced features includes next hop addresses included in the routing updates, use of multicast addresses in sending updates, authentication options available, and just like RIP v1, v2 is distance vector based, and both versions of RIP share the same features or limitations, some people might call it, such as use of hold down and other timers to prevent routing loops, use of split horizon or split horizon with poison reverse to also prevent routing loops, and the use of triggered updates when there's a change in the topology for faster convergence, and a maximum hop count as well of 15 hops. With a hop count of 16, it generally means it's a significantly unreachable network and it's probably not worth using. EIGRP. EIGRP is the Enhanced Interior Gateway Routing Protocol. It's a network protocol that lets routers exchange information more efficiently than earlier network protocols. It's the responsibility of a router to determine the best path across a network to send packets from the source device to the destination device on a different network. The basic information that routers need to route packets is the destination address, the best route to each remote network, possible routes to all remote networks, neighbor routers that can inform about other networks, and a way to maintain and verify information. The routers use routing tables to determine the best path to the destination device, and the routing table is a map of internetwork that describes how to find a remote network. A network directly connected to a router can be easily used by the router to send information. However, if a network isn't connected to a router directly, then router uses a neighboring router to get information about the remote networks. The routing table can be created through static routing or dynamic routing. In static routing, the network administrator types information all about the remote networks in the routing table manually. Each time the network information changes for a network, then the network admin must update the routing table to ensure that the routers get the correct information. In dynamic routing, the routers access neighboring routers and update each other's routing table information using common protocols. This way, the routers on a network update their own routing tables with all remote networks, and whenever a change occurs, the router dynamically updates their routing table and informs other routers around it about the change. So how do routers determine the best path to the destination? Well, as soon as a packet is received by the router, then the router compares the destination IP address to the packet with each entry in the routing table to find its best match. Once the best match has been found on the router, then the router picks up the interface to be used and forwards the packet, and then encapsulates the packet into the data link frame and forwards the packet to the destination network interface. So we know that routers operate in layers 1, 2, and 3 of the OSI model. However, they are called layer 3 devices because they take their main packet forwarding decision based on the information available in a layer 3 IP packet. So the router encapsulates the layer 3 IP packet into the data portion of the layer 2 data link frame and then forwards them to the appropriate exit interface. The encapsulation is required because the entry and exit types of the data link frame may be different, and the frames may be received in one type and sent in another type. For example, the router may receive a data packet encapsulated in the Ethernet frame and may encapsulate it into PPP when it forwards it. The encapsulation of packets gets different in the data link layer because the encapsulation depends on the interface type of the router and the interface type of the transportation medium it's sent on. So the examples of different data link technologies connected by a router would be Ethernet, HDLC, ATM, WAN serial, such as like T1 connections using PPP and frame relay. So routing is a process that is run using protocols such as OSPF, EIGRP, BGP, and the routing protocols configure routes in the routing table for the destination and assign the administrative distance. The accepting and replying process of the routing table. The routing table accepts the information from the routing process and then forwards the information to the forwarding process. Then we have the forwarding process. The forwarding process accepts the information from the routing table and then makes a decision based on the its routing table. It forwards it to the destination. So while building a routing table, a router considers the administrative distance, which is the shortest administrative distance, and is given a preference while deciding a route. So if you type the command show IP route on a router, then you can see the route configured in the routing table here. This is the key, and this is what the route should be underneath here. You have C, which is directly connected, and it's on Gigabit Ethernet and port number 19, switch number 2, directly connected, and then that's available via that, etc., etc. So as far as OSPF goes, you have different OSPF areas, and you can link areas if you want to, or you can include them all in like an area 0. So here, if you wanted to, you could extend this big green area 0 across all 3 routers, which means each router would have area 0, and the one on the left would have area 1, and the one on the right would have area 2. And it's impossible for them to communicate like across areas without having a linking area. So as it is here, area 1 couldn't communicate directly with area 2, it would have to go via area 0.